There we go. Okay, so for number 6, from the homework, just a couple of brief notes, and then we'll see if you have any further questions. So number 6, equivalence, relation, and then partial order. So those two words were in there, or those phrases. So an equivalence relation is like equals. It's a relation that is symmetric, reflexive, and transitive. So symmetric, reflexive, and I believe that if it's those two, then you're guaranteed that it will be transitive. Transitive. So that's an equivalence relation. You can think of equals or anything that you would think of as being equivalent. For example, if we wanted to say that, I don't know, that anyone who is, like people in this class are all in a little club. And, being in this class makes you part of this equivalence, I guess. Yeah, I guess any class would be like that, wouldn't it? But anyway, so symmetric, reflexive, and transitive, the equals. Equals is a good example of this. If you have two variables that are equal, and then a third that's equal to one of the two, it'll be equal to all of them. So you have this like club that you're put into. Partial ordering, on the other hand, is anti-symmetric. Reflexive, and transitive. So a good example of this is, so you have the equal sign over here, something like this. Less than or equal to is a good example of a partial ordering. So the phrase itself, even partial ordering, it makes it sort of points you to this, that you're ordering things, but not everything is ordered to everything else. With the less than or equal to, pretty much everything has a relationship with everything else, but that's not the case with all partial orderings. For example, let's see, if I do A is related to B, means that A is a divisor of B, then that's a partial ordering as well, because everything is a divisor of itself. And if you have one divisor of a number, like say 6 is a divisor of 12, every divisor of 6 is also a divisor of 12, so you have transitivity. But there are certain things like 3 and 4 are not related to one another. 3 is not a divisor of 4, and 4 is not a divisor of 3. I just wanted to point out that you didn't, that's unlike this. That's still a partial ordering. So you don't have to have a complete ordering like you would with the less than or equal to. So it's partial ordering. Some things are related to others, but you are anti-symmetric because if 6 is a divisor of 12, 12 can't be a divisor of 6 unless you were dealing with the same number, like 5 is a divisor of itself. So anyway, that hopefully will explain the deal with number 6. But does that help you sort out? Let's see, it's which of the relations in 5 are partial orders. Are you able to sort that out? Basically, if you have answered question 5, which is reflexive, symmetric, antisymmetric, or transitive, determine which ones are which. Just pick the ones that are both reflexive and symmetric. Those will be equivalence relations, and the ones that are reflexive and antisymmetric will be the partial orderings. So anything else about that questions or concerns? Yeah, I didn't have those. I don't have those words on my quiz. I'm afraid. Don't be afraid. So we got a quiz? We got a quiz. Let's do it. That's the big ones. Over there. It looks like people are finishing up. Oh yeah, I forgot. There is a homework. I guess I can collect that as well. So when you're done, you can send the homework over into the middle. You can send the quiz over to the middle, and then we'll get the answers here in just a minute. This. Bring everything. that? All right, I think I got everything. So we'll whip through this real quick because it's not that hard. Reflexive, no here. So remember, reflexive just means that everything is related to itself. So here, this isn't reflexive either. This one's reflexive, so I guess I'll go down. This is a no, this is a yes, this is a yes. Symmetric means that everything has its reverse, so those all have their reverses there. That one's a yes, this one's a no. This one I think is a no, and then this one's a yes. Antisymmetric means that none of the reverses are there. So if you're symmetric, except for this last one, you can't be anti-symmetric. So here, because the 1, 2 and the 2, 1 are both there, you can't have, this can't be anti-symmetric, so that's a no. This one, though, is fine because there is no 2, 1, there is no 3, 1, and so on. So this one is yes, anti-symmetric. This next one is a yes, anti-symmetric. And oddly enough, that last one is anti-symmetric, kind of vacuously. I know that's ridiculous, but technically it is. It fits the definition. So, and then transitive. So if you chose no, it's totally understandable for that last one. So the next one, the transitivity, that one's harder to evaluate just looking at something like this, and that's something we'll deal with today. So after today, you'll have a tool, and you can evaluate transitivity. But for now, just eyeball this thing. This is not transitive specifically because 1 goes to 2, or 1 is related to 2, 2 is related to 1, but 1 is not related to 1, is not part of this first one. So that's sort of what I'm looking for. So here 1 is related to 2, 2 is related to 3, 1 is related to 3. I think that's the only thing we have to check. So this one is transitive. The next one is transitive, I believe. 2 is related to 1, 3 is related to 2, 3 is related to 1. Yeah, everything's good there. That's, whoops, that's a yes, transitive. And then this one is sort of vacuously transitive because there's nothing to check. So there it is. So if you wanted to describe these things, this one here, let's see, partial ordering is this third one down. Technically, this one is a partial ordering and an equivalence relation, which is really ridiculous. I mean, it's a partial ordering, but it's got almost nothing. There's no ordering really. So there it is. All right, let's move on. So as promised, we're going to be taking a look at a way to take composition, yeah. A way to represent these equivalence relations or relations in general so that you can evaluate whether the relation is, I got my reflective thing on, to see if it is transitive relatively quickly. That's sort of the goal for today. And it's going to do its little circuitous route. First of all, I need to mention this, this conjunction or composition operator. You're already familiar with this from your days in pre-calculus or calculus, so let me remind you of this. So let's say that f of x is equal to 2x, and g of x is equal to x squared plus 1. I want to know what is f of g of x. So take a minute, write down what you think f of g of x is. Hopefully you remember. And might as well do this also, g of f of x. So we'll do both of those. And this is just your pre-calculus or calculus definition. And I know it's been, because you guys are all advanced, you probably had this in 6th grade. Hard to remember back that long. Let's see some volunteers here just a second. I'm really excited about this. All right, let's see how we do. John, what is f of g of x for my f and my g here? Very nice. So 2 times the quantity x squared plus 1. One way to think of this is that you're just doing this. This is f evaluated at g of x. And so you just replace all of the x's up here with g of x. And that's what you get. Very nice. All right, let's do g of f of x, just to make sure. Pearson, what's g of f of x?
Just 2x squared plus 1.
And that's the quantity 2x, right? Yeah. 2x squared plus 1. And there again, you're just plugging f of x in everywhere you see an x up there. So very nice. So that's easy enough. When we deal with relations, you can think of the relations as being a sort of a similar situation to a function. A relation is sort of like a function. It has an input and an output. These are way too many words. I don't want to, in fact, I should probably just ignore that. So here's a relation. You can think of these as being relations. That 1 is related to A, 2 is related to B, 3 is related to A, 4, actually these are functions, but relations are special versions of functions. But anyway, so that's like a relation. You can see that there. And then function g is A is related to smiley face, B is related to frowny face, and so on. And so if I did g of f, the first thing I want to make sure is that the output, if you want to think of this as an output, input-output situation, the output for f had better be the same type of thing as the input for g. That's not a consideration when we actually get to the relations, because relations, you're dealing with the same type of thing, both in the input and the output, but for functions it does matter. But anyway, the composition to do g of f, in essence, you're doing f first and then g. And I know that that seems wrong because the g is clearly printed first, isn't it? However, if you think of it in terms of this sort of thing, when I'm evaluating a function like in pre-calculus, you do the f first, this g of f, 2x is evaluated first. It's inside the parentheses. And so that comes first, and then you do the g. So it does feel a little backwards for that reason, but so this is just an example of a function in terms of like something that might be like a relation. Let's take a look at a real relation though, because these aren't relations, these are functions. So let me just switch back over to the quiz here, and we'll take a look at, once I erase this stuff, enough. So let's just take a peek at this right here. So that we're going to call the relation R. And so you can imagine doing this relation R, let's see, and then maybe the next one we'll do is S. S there. So we could do R of S. I guess we have to do S first, don't we? So R of S, the way that this is going to look, that composite relation is going to be the set. And I'm just going to do a few of these, so bear with me for just a sec. So we're going to start with 1 is related to 2, and then you can pick anything down here that starts with a 2, so I'll just concatenate that with that. So 1 is related to 2, but then 2 is related to 1. So we've got 1 comma 1. And then 1 is related to 2, then 2 is related to 2, so I can do 1 comma 2. And I think that's all I can do with that first thing. Then the next one is 1 is related to 3, 3 is related to 1, so I'll get 1 comma 1. Similarly, I'll get 1 comma 3 and 1 comma 2. 1 comma 2. Is that right? Yeah, because 1 is related to 3 up here, and then 3 is related to 2 down here. So you can see already I've gotten something that doesn't exist in R and something that doesn't exist in S. And still it's stuff that exists in one of them, I suppose. But anyway, if you continue in this fashion, eventually you'll get all of the relation R of S. So you're just doing one of them and then the other. It's like playing a little doing moves. This move, pick something from up here and then do something from down here with the result. Input output. Yeah.
So we're like creating a transitive.
It's like a transitive thing. Yeah, yeah. Where you're doing one thing and then the other thing. So that's a good way of putting it. This doesn't guarantee that the result will be transitive, but it is like a transitive thing. So yeah, maybe it would help to, let me just do one more here, starting with 2, 3. We can do this, we start with 2, we go to 3. So here, let's do it this way, 2, 3, and then that comes from up top, and then 3, 3 from the bottom gives you this. And then if I did 2, 3 from the top, and then 3, 1 on the bottom, I'll get 2, 1. And if so, I'm just taking this 2, 3 and concatenating it or doing it next to one of these other things. So it's like you do this move, and then you do the second move. I don't like that one, so we're going to go on. Okay, so we're getting there. So that's the first thing to note. I guess just that there's this idea of being able to do a relation over again. And yeah, I guess the idea that this is transitive, that's sort of the goal of this, is we want to know whether or not we have a transitive relation. And so this is getting us closer to that. So now how are we going to represent this? There's two ways we're going to represent this. There's the graphing way, and then there's the matrix way. So I don't want to dwell too much on the graphing way because even though it's useful, it's not going to be as useful for what we're doing today. But just to show you what we mean by this, graphing, to graph a relation, what you do is you put dots down. So this is like your finite state machine thing where you've got different nodes, but here they're just dots, and those dots represent the different points that you're relating to one another. So you have A, B, C, and D. So I'm going to have point A, point B, point C, and point D. And then I'm going to put arrows. So it's a digraph, which means it's a directed graph. And the arrows are just going to point from one of the things in the relation to the other. So A is related to B, and so we're going to have this arrow pointing from A to B. You could probably fill in the rest of this yourselves. Let me just do one more, and then I'll let you do the rest. So A is related to D means there's an arrow from A to D. I'll bet you can guess what BB is going to look like. It's just going to be a loop going around from B back to itself, similar to our finite state machines when you had a loop that went from a state back to itself. So there's what, 5 more? Well, 4 if you've done the loop for BB. See if you can fill in these other 4 yourselves, and then you can compare with what I have. I'll show you mine in just a minute. I'll have to make my arrowheads bigger next time, so sorry about that. It's kind of hard to see them. Okay, so hopefully you've got the other 4 arrows. I'll show you what my other 4 arrows look like. I've got this arrow going from B to D. I've got another arrow going from C to A. I suppose you could have chosen to put this around the outside so that it didn't cross the BD arrow, which is fine. I've got an arrow from C to B and an arrow from D to B. And that's it. So there's all my arrows. So did you get something similar, hopefully? If not, hopefully you can identify where yours is different. Now the reason that this is useful is because if you want to think about um, composing two relations or composing a relation with itself, essentially what you're going to do is you're just going to go two steps along this relation. So, for example, R composed with itself is going to just be what you get if you take two steps, two arrows. In other words, let me just show you what this means. So R composed with itself, you do A to B, and then you go along one of the other arrows, let's say from B to D. So there's one of the relations that's in, so this would be A is related to D, is what that's representing. It's like you're just going two steps. Starting here, let's take two steps and see where we end up. Not very convenient for checking to see if something is transitive, because, well, here's the idea, is if after taking two steps you always end up with a relation that was in the original, then you end up with a transitive relation. But it's still not super convenient because it requires you to check a whole bunch of stuff, and it's kind of difficult to do. So is this transitive? If you were to do this R composed with itself, going along two arrows, do you get anything new? Is there anything new that shows up that wasn't in the original? It's kind of hard to tell. There it is, yeah, C to D shows up. So here, just in case you didn't see it, I'll highlight this one. If we do C to A, so remember two steps, 1, 2, you end up with a new edge that wasn't in the original graph. And then, so this thing is non-transitive because C to D isn't up here. So specifically what that's pointing out is that C to A, C is related to A, and A is related to D, but C is not related to D. So that's the deal here with this transitivity thing. So you would think that if C is related to A and A is related to D, you would think that C would be related to D, but it's not. But it is in the composition, so that's not transitive. All right, let's see how you do with this. It says group work, but it's really just one for you to do yourselves, is just construct this graph for this relation, see how you do with it. And just so you know, the one that I drew, I'm looking at it, I realized I did it a little different. I have 1 and 2 on top, so 1, 2, and then I go down below 1, I put 3. So it's 1, 2, and then 3 and 4. I got wrong. Just so that we all have something similar. Oops, not like that. In a second. So 1, 2, 3, 4. Instead of continuing around clockwise, I kind of did it. So if you start with this, you'll get something similar to what I've drawn. But yeah, work with a friend if you want, or just work by yourself. Some of you look bored. You've probably done it already. Let me show you what I got, just so that you can compare. And you can complain if I get any of this wrong. So there's my matrix. Or not matrix, sorry. I'm already ahead of the game here. My digraph.
Are the arrows required
What do you mean by required?
Like to show this relation is going to goes from here to there, like 1 to 1.
Well, yeah, certainly this is not symmetric in the sense that 1 is related to 2, but 2 is not related to 1. In fact, it's anti-symmetric. And so, yeah, the arrows are important for that because it shows what's, yeah, 1 is related, like, yeah, that's a good example here. 1 is related to 2, but 2 is not related to 1. If it was, you would have another arrow going back. I suppose the loop, which I didn't even put an arrow on the loop, that's unnecessary. You can go either direction on the loop. But yeah, those other, yeah, you need the arrowheads telling you which direction these point. The other comments? That's a good point. I mean, it's a good, I guess, thing I just realized is that looking at this, you can tell for sure that this thing is anti-symmetric. You can also tell that it's not reflexive. For it to be reflexive, it would have to have a loop on each of the points. Transitivity, though, is a little bit harder to evaluate at this point, but we'll get there. Oh, I guess, yeah, it's still going to be a little bit tricky. Actually, I can tell for sure it's not transitive. Just one bad combination spoils the whole thing. So just find one counterexample. So 4 is related to 1, 1 is related to 2, but notice that 4 is not related to 2. The other, 2 is related to 4, but 4 is not related to 2. So this is not transitive. But it still feels like we're just eyeballing it here. It's hard to tell, is this transitive or not? So we need something a little bit better. But we're going to use this to represent relations, especially when we get to relations among finite state machines. So here's how we're going to do this here, and also this will help us with the finite state machines as well, is we're going to make what's called an adjacency matrix, which is going to be a much bigger structure, if you will, but it's going to allow us to keep track of all of the stuff going on within the relation and actually be able to evaluate something like transitivity super quickly. So anyway, what we're going to do is we're just going to make a matrix and have the different elements of this set here along the side and top. And anytime you have a relationship, you'll put a 1 in the row and column for that particular relation, and then zeros everywhere else. It's just zeros and ones. So it'd be helpful if we had an example. So here's an example. So I've got the numbers 1 through 5 are my set. The relation is that x is related to y if x minus y is a multiple of 3. So you can kind of imagine what this means. It means that 3 is related to, 3 is not related to anything. Well, 3 is related to itself. 5 is related to 2. 4 is related to 1. But not a lot of things are related here. So let's see if we can represent this. First of all, 1. Is 1 related to itself in this? I don't like the way that this showed up. Just a minute. I'll make this bigger. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I've got my little grid here, an array. And I'm just going to put a 1 when the two things are related. And I'm going to put a 0 if they're not related. And I'll make this look better in just a minute. Okay, so is 1 related to itself? Well, what's 1 minus 1? 1 minus 1 is 0, and 0 is a multiple of 3. 0 is a weird number. It's a multiple of every number. I know it's weird to think of that, but because 0 divided by whatever is still 0. The definition of divisibility is that you can, well, technically it's that something can be multiplied by an integer to get the number that you're interested in. But yeah, 1 minus 1 is a multiple of 3, so I'll put a 1 here. Let's make that a different color. Blue. There. Okay, so there's a 1. What about 1 and 2? Is 1 related to 2? Well, 1 minus 2 is negative 1, and negative 1 is not a multiple of 3. So that's going to get a 0 there. I'll do this top row, but then you're going to do the rest for me. Is 1 related to 3? Well, 1 minus 3 is negative 2, which is not a multiple of 3. What about 4? 1 minus 4 is negative 3. Negative 3 is a multiple of 3. It happens to be negative 1 times 3. So that's going to be a multiple, so that'll be good. And then 1 minus 5 is negative 4, not a multiple of 3. All right, so see if you can fill in the rest of this, and there will be a pattern that will emerge pretty quickly with this particular grid here, this array. I'll give you a minute, see if you can do it yourselves, and then we'll compare. I'm sorry?
So we're going to end up with a diagonal column.
You sure are, yeah. One of the things with this particular relation, not all relations are like that. All right, let's see how we did. I'll just fill this in. This is going to be a 0, but let me know if any of these look wrong to you. 0. This is going to be a 1. 0. 0. 1. 0. Does that look right? It's sort of this interesting tri-diagonal, if you will, or it's not really a tri-diagonal matrix. It has 3 diagonals of 1s. So interesting. Okay, so there we go. Here's a better rendition of this right here. And then over there, I have the matrix represented. So this is kind of an array. And the matrix itself, I've got the indices, if you will, written above and to the side, but those indices are not part of the matrix. The matrix itself is that, the stuff without those indices. So that itself is the matrix representation of this relation. So it's just a bunch of zeros and ones, a 0 if the two things are not related, a 1 if they are related. And I suppose we have to establish, if we're going to leave off these indices here, we have to establish what order we're going to put the elements in for the matrix. That's not as important for this transitivity thing, though. So, all right, there's one more piece to this puzzle here, and that is multiplying matrices. So I need to remind you how to multiply matrices. You've probably done this before if you've had linear algebra at some point, or if you've had any more advanced algebra, you've probably multiplied matrices. But here's just a reminder, and our matrices will all have zeros and ones. Oh, and by the way, when you have a composition of 2 relations, you just multiply the matrices together to get the matrix representation of the composition. We'll see exactly why this is in just a bit. Well, here, I'll just remind you of the combining, the multiplying. So if you're combining the 2 relations, and I've just got 2 simple relations here, simpler, you're going to multiply across and down. So what I mean by that is this, across and down. You probably remember doing this, so I'll just do 1 times 0 plus 0 times 1 plus 1 times 1. Do you remember doing this? And that is going to be the first entry in this particular matrix. So that's what that looks like. I'll go through this pretty quickly. I'm hoping it's a reminder, but if you have never seen this before, I guess it's not hard. The pattern is not hard to see. So this is all matrices. When you multiply them, you do this same type of a pattern. No matter how big they are, let's go through and multiply. Anyway, that entry, that's going to be the top left entry. So you're always going to go with the row that you multiplied and the column that you multiplied to figure out what entry you're working on. So that's going to be that 1 right there. Now, I know this is going to be tedious, but let me do some others. To get the next entry, I'm going to multiply the top row by the middle column. So when I do that, I get this. So that's 1 times 1 plus 0 times 0 plus 1 times 0. So hopefully you see where all that. If you're seriously confused, though, let me know, and I can color code things or do a different example. Because the ones and the zeros, sometimes you get lost as to, wait, which one is that and which of the zeros? So I'm happy to try to make it a little less ambiguous. So yell out. Okay, I know it's early. No yelling. All right, the next one is going to be a 1 as well. There it is, very nice. Okay, let's do this a little quicker. This is the middle row with the first column. When I get done with that, I get 2. I know these are supposed to be 1 and 0, but we'll get to what 2 means in just a minute. If I do the middle row with the middle column, I get 1. And then the last one, I get a 2 as well. Finally, the bottom row, I'll just do all 3 of those at once. Bottom row with the first column is 1. Bottom row with the second column is this one, it's 0. And then the bottom row with the third column is this math here, and that's also 0.
What if you get a 3?
You could get a 3. Yeah. If you had a larger matrix, you could get a 4. So we got to talk about what does that 2 mean there. So does anyone want to guess as to what the 2 means in the context of a relation? So these are just matrices, and this is how you multiply. But they are going to, eventually, we're going to talk about them in the context of a relation, like this relation. So what would a 2 mean if I got a 2 if I took the matrix representation of this? Let me erase all this. Let me see if I can. Let me see if I can find one that has a 2. Oh yeah, CD. CD. So C to D is going to have a 2 for this. If I were to write the matrix representation and then actually do the multiplying of the, like compose the relation with itself. So does anyone understand why or see why CD would have a 2 instead of a 1? Any guesses? Doesn't have to be the right answer. You're probably right though. So you remember that we determined earlier that CD, so C is related to A, and A is related to D. So CD would show up in the composition of this with itself. But check this out. That's not the only way to get from C to D in 2 steps. You can also go this way. So this composition matrix actually counts the number of ways that you can get. So that 2 there just means that you can get from, let's see, where is it? Where's my final answer? There it is. So that those 2's just mean that there are 2 different ways to get, there's 2 different ways that 2 is related to 1. So the second thing is related to the first thing. So it's always row, column. And there's 2 different ways that the second thing is related to the third thing. But we don't really care about how many ways there are. And so just if we're talking about a Boolean matrix, you could think of this as being an OR. That is to say that all we care about is that something is true, not how many times it's true. And so when you're thinking about adding up, instead of thinking about adding them, just think of ORing them together. So when you're multiplying and adding, instead of multiplying and adding, you multiply and just say, is there a 1? Is there at least a 1? And so all of those 2's become 1's, and we're happy with that. And so that's what the actual composition of these 2 would be. So let's get back to the whole business of whether something is transitive. So here we go. Let me go back to this matrix. I can find one that works there. Okay, so here, this matrix. So to figure out if you have a transitive relation, all you got to do is find the matrix and then do the composition of the matrix with itself. And as long as the result is a subset of the original, then you have a transitive matrix. So let's see, where does it say this? I thought I had it written somewhere. Apparently I did not. I thought I had that written somewhere, but apparently I didn't. So I'll just write it over here. Is that if you do this, so let's call that matrix A. There we go. So we'll call that matrix A. So A is equal to that matrix. So if A times A is a subset of the original matrix, then the relation is transitive. And here we're thinking of matrix multiplication in a Boolean sense. Boolean meaning all we care about is whether there is something in each entry. So if it's a 1, a 2, or whatever, we're just going to make them all 1's. So let's think about this one. Is this multiplied by itself going to be a subset of the original? So let's do that. I'm just going to rewrite this. 1, 0, 0, 1, 0. I swear that I had that typed up somewhere. I just can't find the slide for some reason. 0, 0, 1. There we go. Uh-oh, I've missed a line. 0, 1, 0, 0, 0. It's kind of hard if I don't have it written up correctly. So at this point, it would be a pain. I don't think that we want to do the whole thing, but let's just go ahead and do a few of these. If you multiply the top row by the first column, you get 2. Because 1 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 1 plus 0 times 0. And if you turn those pluses into the Boolean or, then you basically have 1 or 0 or 0 or 1 or 0. You have at least 1 there. And so the answer will be a 1 for that top row, top column. This will be a little tedious to fill in, so I won't do the whole thing, but I'll do the next one. It's going to be a 0. You can double check this. That if you do top row times the second column, nothing lines up. 1 times 0 plus 0 times 1 plus 0 times 0 plus 1 times 0 plus 0 times 1. You get 0. Anyway, when you get done with this, from a Boolean standpoint, you'll actually have the original matrix, which means that this thing, although you probably intuitively could have told me this, that thing is transitive. So if you can multiply the matrix by itself and get a subset of the original, then for sure it's going to be transitive. And you know, I sense that probably this would be really easy to implement in Python. We got some Python skeptics here. I actually reached out after we chatted, and I've already gotten some responses on Teams from Curtis and Dr. Rock.
Excuse me.
Yeah.
The bottom sentence there says if A times A is a subset of A, then R, what is that?
It's transitive. Sorry, transitive. Yeah, I know I had this typed up. Just a minute. If I put my glasses on, it'll come apparent. So weird. Well, I don't see it. Maybe it was just in my fantasy land. Oh well. Okay. Good enough. All right, so homework should be, hopefully I've gotten everything with the homework. If not, I will apologize on Friday. So stick around if you want to chat. Otherwise, look at this. You got plenty of time to get to your next class. And I will continue to see if I can get some clarity on the Python thing for all of you data scientists. So we're going to stop streaming.